Welcome back to week 9, vibration isolation. All right, so there was a statement in the book, and I mentioned it before, about something about the square root of 2. And we noted from some graphs from Dr. Jasinski's notes that the square root of 2 seems to have some significance as the crossover point. And I saw this problem in Beer Johnson that dealt with this. So let's go through reading time. I wanted to cover this. Show how springs can be used to support a block in two different situations. In figure 1, they help decrease the amplitude of the fluctuating force transmitted by the block to the foundation. In figure 2, they help decrease the amplitude of the fluctuating displacement transmitted by the foundation to the block, right? So this one, we're moving up and down, and we want to stop, or we want to decrease that force from here to there as the vibration isolation. Or it could be that the ground is moving, and we don't want the block to move as much as the ground underneath it. So you can kind of picture those two scenarios. There's a good thing to know about. And in this, we don't have to worry about damping, which is kind of nice. So the ratio of the transmitted force or the ratio of the transmitted displacement is called the transmissibility, that's the topic we're working on, the topic du jour, which is also a kind of soup. Derive an equation for the transmissibility for each situation. Give your answer in terms of omega f, omega n, which is, of course, r, of the frequency omega f of, of the frequency omega f of the impressed force or impressed displacement to the natural frequency omega n, which is, okay, we knew that already, of the spring mass system. Show that in order to cause any reduction in transmissibility, the ratio omega f, omega n must be greater than square root of 2. That's a lot of words. So you might want to replay that, but basically, or just watch what's going on right here. So for situation 1, well, let me write down this. Okay, so first, the basic equation without any damping is going to be the force, and they're using PM, so I'm going to go PM, divided by K, 1 minus R squared. So we're going to show that, but this is where we're going to start from. So we're already assuming that we know this thing right here. We don't have to derive it. It's always bothered me when you've had problems like that. They don't really tell you where your starting point, but I can get over it. So the FT that we're going to have is going to be equal to KX, right? As a value. That is just that is just truth, right? The transmission to the ground, which is going to be equal to, recognize that's going to be equal to PM, but I'm going to put it, but I'm going to put the K over to the side, and I'll go PM over 1 minus R squared. So in this case right here, we get rid of that. So now we have X in terms of PM, all right? And so our transmissibility is going to be FT over PM, which is just going to be 1 over 1 minus R squared, which is the thing we were trying to get. I know, it seems kind of stupid. That's what we're trying to do. Okay, so 2 right here, we're going to say that, well, we recognize that we have a relationship of del M over 1 minus R squared instead of this guy over here, right? So an equivalent thing was placed over there. So it really appears to us in terms of our first thing that we're trying to load, that we already did that pretty easily, that our transmissibility is now going to be TR is going to be X, which is our output, divided by our del M, which is equal to the same thing, right? So they're showing, I guess the first part was to show that the transmissibility is the same relationship with respect to well, they were saying omega F and omega N, but we know that's the same thing as R. All right, so we did that first part. So let's say that the what's going to happen when transmissibility, all right, so in this last part, show that in order to cause any reduction in transmissibility, that the ratio must be greater than 2. So let's say that if transmissibility is equal to, let's say, 1, you'd have 1 over 1 minus R squared, right? This, of course, is different than this equation right here, right? Because we reversed the order of stuff. But we haven't made that decision right here. So let's say that if it's equal to 1, you end up having 1 minus R squared is equal to 1, right? So if you bring 1 over to the other side, it becomes 0. So R is equal to 0, which is a nothing burger. So just remember, well, the other option is to make that negative, right? That absolute value of the thing means it's plus or minus, and therefore what you have is a minus 1 plus R squared equals 1. So R squared is equal to 2, so R must be equal to the square root of 2, right? So the only way that you could get a reduction out of this is to have to get transmissibility to be less than 1 is to have R be something that's greater than the square root of 2. That's like the concept that we have right here. That's where the square root of 2 comes from. So, lot of talking for little reward right here, but it kind of comes back to where that square root of 2 comes from for here. It's like right there.